Hello everyone, my name is Kostya and today I will talk about chemistry. I want to help you to understand how to solve for hydronium ion concentration and pH using by K expression at equilibrium. For this we need our pen, paper and question that we will solve. Okay, let's do it. The first what we should do is read a question. Just read it. Calculate the hydronium ion concentration and pH of a 0.10 mol per liters solution of nitrous oxide. Okay, we read our question. The next step, we should write our reaction. Our reaction is the nitrous oxide HNO2 aqueous react with water plus H2O. Why with water? Because in this question we have only one reactant and we can react our oxide at equilibrium with the water at any time what we want. At any time. We use a two sides arrow like this at equilibrium and it's equal to hydronium ion H3O positive aqueous and NO2 aqueous. Don't forget about charge, is negative. This reaction actually reacts less than 50%. Why less than 50%? Because when we use our data booklet, we open our oxygen and base table. We knew at equilibrium system, if oxide is upper than base, that means reaction is greater than 50%. But at this point, our oxide over here and our base, actually with water like a base, our oxide is above the base. That means its reaction react less than 50%. Okay, let's do next. Next step is we are creating ice table. Ice table means initial concentration, change of the concentration, and equilibrium concentration. Initially, we have our oxide is 0.10 mol per liter. For water, we do not use ice table. If we have initially our reactants, that means on the product side we have a 0. Our change, we don't have any change in our question. That means we put x, but not just x. We put negative x. That means we lose on the reaction side and we gain on the product side, because if we lose on the left, we should gain on the right. This means plus x and plus x. Next step is do our equilibrium. We just do easy step. 0.10 minus x. It's equal to 0.10 minus x. Over here, 0 plus x. It's equal x. And the same as here. Over in this question, we use our oxide. And we have a hydronium. That means this change, this x. The x is equal to our hydronium concentration. That's what we are looking for. We're looking at our change. And changes our hydronium concentration. This change, the hydronium ion concentration, is that small that we will not see it. And when we use our K expression, we'll get messed up with this axis over here, and it'll be hard to understand what is going on. I will show you. When we use our K expression, we use the numbers from equilibrium. K expression, Ka is equal to the concentration of oxide, is equal to products over reactants. That means H3O positive aqueous times NO2 aqueous negative. divided by HNO2 aqueous and nothing, because in our K expression at equilibrium, in Ka we do not use two states, liquid and solid. And over here, just put everything what we have. Ka is equal to X for hydronium plus X for NO2 divided by 0.10 minus X for our nitrous oxide. But to make our life easy, this change of X, our hydronium concentration, is that small that we'll not see these big changes in our numbers. And we can just cross it out like this. Just cross it out and we will make our life easy. That means Ka, the concentration of oxide, is equal to X squared over 0.10. Right now, become more interesting. For solve for X, we should know this number and this number. And we know them both, because Ka of nitrous oxide is 5.6 times to 10 power of negative 4. How do you know? Again, I use my data booklet. I open my oxide and base table. In our oxide and base table, we can see the name of the oxides, oxide formula, conjugate base formula, and our Ka column. We're looking for our nitrous oxide and just looking for the last column. And it's equal to 5.6 times 10 to negative 4. That's our concentration of our oxide. Okay, that means 5.6 times 10 to negative 4 is equal to X squared over 0.10. Actually, we don't need any. Again, we don't need this. Over here. 5.6 times 10 to the negative 4 is equal to X squared over 0.10. Right now we use our math skills. The first we should get out of the fraction. We just times each side by 0.10 times 0.10, and it's equal 5.6 times 10 to negative 4 times 0.10 is equal X squared. 5 points, and we times these two numbers, and it's equal to 5.6 times 10 to negative 5, and is equal to X squared. Right now we should get out of square. We use our square root. We just squared each side, and it's equal. X is equal to 7.483 blah 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 times 10 to negative 3. This number is so long that I'll have no space to write it. I just use few numbers and keep it in my calculator all these numbers. How we said previously, our X is equal to our hydronium ion concentration. This means hydronium ion concentration is equal to X, and X is equal to 7.483 blah 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 times 10 to negative 3. But if we see previously in our question over here, we have only two digit numbers. It's 1 and 0. This means over here we should have only two numbers. It's equal to 7.5 times 10 to negative 3. Okay, we find our first thing. The second thing what we're looking for is our pH. We know one formula. The formula is pH is equal log of hydronium ion, negative log times hydronium ion is equal pH. We have our hydronium ion. That makes our easy life. Negative log out of 7.5 times 10 to negative 3 is equal 2.13. Or here, don't forget about your initial, that's mole per liter. Over here in pH, remember, in pH, we count our significant digits after this point. Before this point, any numbers, they doesn't count. After this point, we count our numbers. It's 1, 2. We have 2 digits. That's it, guys. Thank you very much. Sorry for my language. And see you on next week. And after we'll talk about some crazy biology stuff.